Hi, everybody. Welcome to Lesson 1. And kind of extending off our preamble PowerPoint that I had posted earlier, what I wanted to do with this section here is describe statistics in context. And I think it's really important. If we examine statistics simply as an entity unto itself, it simply becomes a series of equations and mathematics. So what we have to understand is, how does statistics actually fit into the research paradigm or research methodology? And I put a little funny quote on there, trying to understand statistics without understanding its place in research is like trying to extract flour from bread after it's been baked. And it's true, right? These two things kind of go hand in hand together. So that's what I want to do with this session. How do we see statistics in context? How do I make sense of these things, and how do they operate? And so here's our outline for this session. So we're going to begin with statistics and research. I call that T for 2 and 2 for T. We'll get into a little bit on measurement and statistics, which I call garbage in, garbage out. And then we'll spend the last two sections on the types of statistics, which are going to be descriptive statistics and what we call inferential statistics. And a bit of a funny one near the end, and it's called sampling and statistics. And there's a bit of a methodology to my madness. In part, I'm easing you into things, but I also want to begin to show you how, even as an undergraduate, or even if you've taken a course in basic statistics, you can begin to develop some areas of critique. Right? Understanding is a big part of statistics in terms of reading the literature, of course, but you can even begin to understand how one can critique statistics if you take a look at things like measurement and sampling. Right? We don't often associate those things with statistics. We think about statistics as, well, these are numbers. Well, you've got to get the numbers from somewhere. So where do you get the numbers from? That becomes the question. So we'll attend to that a little bit later on. So this course is Psych 207, and it is a data analysis, and it is aligned mostly towards, well, for psychology students. I recognize I've got some nursing students and some human kinetics students, and I think I've got human services students and probably others. My apologies if I don't mention you by name in this class. But a lot of these fields deal with human behavior at some level, right? There's the psychological side of things. There's also the physiological, sociological, even combinations thereof. So a lot of us in this class are really interested in human behavior, and behavior is complex. I have a little bit of background in health psychology, and familiar with some of the theories of behavior change, at least in that field. And behavior is very, very complex. It's very complex. I mean, in our fields, we try to understand behavior. Okay, so why is it that people do things that they do, or why is it that they're not doing the things that they ought to be doing? Those types of questions. We often try to predict behavior. I mean, I think a lot of this is going on right now with COVID-19, and what are people doing when they're when they're socially distancing themselves, especially if they're staying indoors. So it's important for us to know where statistics fit into a research paradigm, or where statistics fit into research in general. So what I've put together here for you is a very, very basic schematic model of how research works. When scientists do their thing, how do they set up that framework? And where do statistics fit into that? Well, usually at the beginning, what researchers do is they spend an awful lot of time plying through the literature. They read an awful lot, and they sometimes will adhere to theoretical models, these types of thing, and they put together a very, very, what they consider to be important research questions for them to answer. These are usually gaps in the knowledge base that are out there. They do a lot of reading, they find the gaps. Let's see if we can't fill in these gaps where knowledge is lacking. And so from that, if the research question is answerable, they put together a series of complex methodologies. Some of these things include sampling, some of them include specific types of equipment, all these things. And it's complicated. It's very complicated. They put together research teams, and they go about and they gather their information. And it's here where statistics fits in, right? Statistics fits in the center there, in the sense that this is where the machinations of all the numbers happen. So all the numerical information is garnered from the participants in the study, and then we use statistics to actually answer the research questions. From that, you get your results in the literature or from the research. We make some conclusions from the statistics. And what that does then is the results from the findings, we then, if they're strong, that is, I mean, sometimes you can have results that can be comparatively weak. We have these conclusions, and then these findings, again, are applied to, or they inform practice. That's generally how it works. Sometimes findings don't apply directly to practice. They're simply filling in parts of a puzzle. And so statistics kind of fit somewhere in here. In reality, they're actually part of the methodology. I just kind of pulled it out of the methods themselves. But that's where statistics fits in. You can't really run statistics unless you've got that base, the research question, and the method set up ahead of time. That's just how it works. And so it fits into something. You can't simply understand statistics in a siloed methodology, right? It's not, you can't study it on its own, otherwise it becomes a math course. But the important thing about statistics, and I've drawn another arrow here, is that it gives confidence in the research findings. That is to say, whatever we found here, we're pretty confident it's likely to be the case, or it's likely to be true. And that's actually really important. If you don't have confidence in your findings, how on earth can you then extend it to an informed practice? It becomes rather serious when you think about it, when you're spending millions and millions of dollars in research. And what if the research is incredibly serious? I mean, I don't want to draw everything to the whole COVID-19 thing right now, but there's an awful lot of research that has been ongoing the last number of months. And the researchers better get it right because the implications are rather serious. So this is where statistics fits into a research model. So after that previous slide of all this integration of statistics and what they do, I give you this slide here. And this is a bit of an odd one. It's kind of like bait and switch here. But it's a great little statement by William Watt, and it says this: do not put your faith in what statistics say until you have carefully considered what they do not say. And that's one of those weird things where you're going, oh, Professor Bodner, what are you doing? Just give it to me straight. But it's not a bad segue into the next slide. Because although I mentioned what statistics do, they kind of give us confidence in what we've found. It's the way we kind of have to interpret the statistics. And it's a little bit upside down. The next slide will show us this. So I'm just going to go out and say it and tell you what statistics do. And it's a bit weird the way I'm going to say this. Statistics don't prove things. As a matter of fact, they work best when they are used to disprove things. Now, that kind of seems a bit unfair because in the previous slide, I showed you this model that flowed in one direction, and it seemed to imply that statistics helps us to answer these questions. That is to say, it helps prove what we think is actually the case. But they don't. They actually work. They work in the opposite way. They disprove things, and students don't like this very much, especially if you're taking statistics. Kind of sounds like I'm doing a bit of a bait and switch here. Well, you told me one thing and really you're telling me they're doing something else. And this is hard. This is a bit challenging, and this is one of the challenging things conceptually about statistics that students have to wrestle with. And I'm in the same camp with you. When I had to learn this. But let's look at statistics a little bit differently. So if statistics can disprove things, how then can we work that to kind of answer our research question? Well, it kind of goes like this. If we can disprove something, right, then whatever is left over, this is probably the true state of things. If we can disprove something, then whatever is left over, this is probably the true state of things. So in some ways, we're trying to prove things indirectly, although we still can't say the word prove. We might use the word this is likely the case or this is probably the case because we disproved this thing over here. This diagram might help us a little bit. Let's say that I'm trying to answer a research question, and so there's something here that I can't use statistics to prove, but I can use it to disprove it. So I've got the little blue box there, and it's got the D in it. The D stands for disprove. And then I might disprove something else. Then I might disprove something else. Then I might disprove something else. And as I'm disproving things along the way, look what we've done. We've actually drawn an outline of something. And it's this outline in the center, this red box, that is this. If I can disprove stuff around the red box, but I can't disprove the red box, then it's likely that the red box actually reflects the true state of things in the world. And so it's kind of like, I'm not sure if you've ever seen artists when they're drawing and they actually won't draw in the center and work outwards. They'll draw on the outside and draw the outline of something. You don't really know what it is until they've done the outline. You go, oh, okay, that's a bird. Oh, that's a cat, or that's a mountain. But they've done it by shading around the area, and that's kind of what we do with statistics. We disprove things, and whatever's left over, that is the likely state of the world or the likely state of things. Right. But this also kind of begs the question a little bit, what exactly are we trying to disprove here? I mean, that kind of becomes the larger question. Well, we can't answer that quite yet. We'll answer that a little bit later on when we get to chapter 7. 7, 8, and 9, we get into what's called the null hypothesis. And we'll talk about the null hypothesis and how statistics disprove the null hypothesis. But we'll do that a little bit later on. Okay, now that I've totally annoyed you here, if we can't use the word prove, and I would say that's verboten. If you use the word prove in any of your assignments with me, I might highlight it and go, you can't say that. What are some of the words that we can use in lieu of prove? Well, we can use the term probability. We can use even adjectives to describe something. There's a high probability or a high chance of something happening. We speak like this all the time, even if we don't use statistics. You take a look at the weather forecast, for example. It's going to be cloudy today with a 40% chance of sunshine. Okay, well, that gives me a piece of information about something. It doesn't give me certainty, but it also allows me to change my actions. Okay, if it's cloudy today, 40% chance of sunshine, I'm probably not going to take my umbrella with me today. We can use the term likelihood. How likely is something going to happen? We can use percentages on top of that to describe it. If I told you, here you go, here's a lottery ticket. You've got a 95% likelihood of winning the lottery ticket tonight. You might thank me very kindly. Oh, thank you so much. How do you know? I've got my sources, right? Yeah, there's a 95% likelihood or 95% probability, it's kind of the same thing, that you're going to be a winner tonight with this lottery ticket. You'd be pretty happy about that if money's important to you. We can also use the terms confidence. Later on in our section, in our course here, we get into something called a confidence interval. And so we can be confident of the findings despite the fact that there's no certainty. And that gets a bit weird and that gets a bit uncomfortable. Confidence without certainty? Yes. confidence without certainty. Think about it when you studied really hard for an examination and you knew the material inside and out. Ever had that happen? Happened to me a few times in undergrad. You study your butt off, and now, do you know for certain that you're going to do well in the exam? No. But you kind of have an idea of what the professor is going to ask. You've studied hard. You're pretty confident going in that, you know what, you're going to get 80% or higher. And lo and behold, you get your exam back, and you got 89%. That's great. But you were confident going in, right? And there's reasons why you might be confident, right? For you, studying hard. It was the fact that the professor gave you practice quizzes. You knew how the professor was going to test. You knew the areas to study. You don't know the future, but you're confident that you're going to do well. We do the same thing with statistics, except we do percentages, right? We talk about percentages. Yeah, there's only a 1% chance here that we actually got this wrong. Right? The flip side might be we're 99% sure we got it right. Now, we're not supposed to do that. We can talk about percentage of how we got it wrong. 1% chance of getting it wrong, that's a pretty low chance. So these are the terms that we can use. Prove means certainty. Right? We've proved it. It's an open shut case. We've closed the case on this. And we can't do that. And there's reasons why we can't say that, as we'll get into, and we start getting into things like in chapter 8, for example, the normal curve. But that's coming up a little bit later on. These next two slides take us back a little bit in terms of some of the research questions we might ask. I don't want to belabor them a whole lot because I do want to move us forward here. But here's some of the things that we do in research, right? We try to make sense of things, both at the individual and the collective level, right? So here's an example. How does the experience of divorce impact the educational progress of children? Well, that's a very, very profound question, and a question that should be answerable. This is an important question. And there are other types of questions along the way, as we'll see on the next slide. Sometimes in research, we develop things to aid individuals. So for example, we might in the psychology field develop both psychosocial and pharmaceutical interventions to help people overcome addictions and anxiety or disorders and things of that nature. There's an example question there on motivational interviewing. But how do we know if we're successful or not? Right? What are the outcomes that we look for success, and how do statistics do that for us? So how does one determine whether or not their intervention actually works? Well, one of the ways that we can do this, and it's the dominant way that we be working with in this course in statistics, is by measuring and using numbers. And this is a bit of a preamble slide to measurement, which is coming up in the next number of slides. But it's amazing what you can find out in terms of changes if you measure something. Right? I mean, that's how you know whether or not you've been paid. If you check your bank balance on a regular basis, you get a sense of what is actually changing. Right? You're paying bills, that money's going out, you get paid, that money is going in. And so you get this running tally of change in your bank account. And we do the same things in our scientific endeavors. We measure things like anxiety, we measure things like depression, all those types of things, happiness, you name it. And then we try to measure change. And we often think that the change that we might see numerically is based upon what we've done with that particular group of individuals, our sample, in terms of our intervention. Right? Then we publish these interventions, and then the interventions might give way towards application in the field. But numbers can tell us whether or not something has changed or not. Now, numbers are not perfect. As a matter of fact, measurement, there's lots of issues with measurement that we're going to get into, and that's a criticism that the qualitative researchers levy at quantitative researchers. They say, well, you know what? There's some limitations to what you're doing. And the quantitative researchers fire back and say, well, same to you. And it's true. There's always going to be limitations. But my hope for you is that you don't run away from the numbers. As a matter of fact, you run towards them. And even if you start things very, very basically. So this is an example of what we call a sociodemographic table. And it's in most journals that you're going to read. The first thing you're going to come across, look at here, table 1, is you get a sense of what the researchers are trying to relay to you, who these people are in that particular sample. Okay, and a lot of times what they do is they simply give you the numbers. Here we go. N simply means for the number of individuals, and percent simply stands for the proportion. This table here, or this column here, is actually really easy to assess if you know what percent is, and most of you do. I would think so. I think 100% of you know what a percent is. You know, I know in this particular sample, 100% of them were female. There are no males in this sample. That tells me something about this particular portion of a population. Now, there's other things here in the sample that you may not be quite sure about here, because we have to get to a place where we can interpret them, and that's my hope for you, is you get to things like the mean and the SD, right? So this is the average and the variance around the average. That's what this means. Right now, it may not mean anything to you, but hopefully by the end of chapter 3, it will mean something to you, and you can actually take a look at even these values here and go, okay, I actually kind of get a sense of what is actually taking place here, even in a simple summary table. So this stuff is actually kind of important. I'm going to show you one more slide on some of the numbers, a bit more complex, and then we'll carry into measurement stuff. This particular slide here is different than the previous one because now we've got a combination of written word and numbers all linked together. And so part of this is, again, similar to what we saw on the previous slide. That is to say, we're seeing some aspect of percentages here, and again, that's fairly straightforward to interpret. But then you get down to something like this here, and this is where students' eyes might glaze over, or they'll simply just skip over it because they don't know what it means, right? Unless you've taken a course in statistics. And so let me just read it out to you. Here it says, factors significantly associated with the DAS21D score included physical abuse. Okay, so assuming that, you know, the researchers have defined what that meant. And then in brackets, here's where it gets complicated and boring, but probably more complicated. Unstandardized beta coefficient B equals 1.68 with a 95% confidence interval of 0.12 to 3.34. Now, the thing is, if you don't know what a beta coefficient is, if you can't interpret a beta coefficient, this is going to mean nothing to you. And it's the same thing with a confidence interval, 95% confidence interval. If you don't know what that means, what this range means, then it's not going to mean anything to you. And you're going to miss a piece of the information. You're going to miss a piece of the information. And so by the end of this course, you're going to know what a beta coefficient is, and you'll be able to interpret what it is. By the middle of the course, you're going to know what a 95% confidence interval is. And that's going to give you some information in terms of what is actually happening when you read journal articles. I know that most of you are probably not going to go and do research, but guaranteed all of you are going to have to read research. So it's in the reading of the research, I think, is one of the fundamental reasons why you take a course in statistics. It develops those critical thinking capabilities. You can gloss over it if you will, but that's like going through writing a paper with one hand tied behind your back, especially if you're going into honors psych, especially if you're going to go into graduate programs. You have to understand statistics. And statistics deals with the numbers, of course. But there are issues with statistics and quantifiable stuff. And so the next slide gives us a bit of an intro into where and why those problems exist, and that gets into measurement. And so for us in Psych 207, in the quantifiable sciences, which is what we're working with here, we deal with numbers. We're not going to deal with the qualitative side of things in this course. It's all about measuring things and using numbers. You can't run statistics if you don't have numbers. To get the numbers, I have to measure them. And so this is the segue into the next section on why we have to pay attention to measurement. It's a preamble. It comes up a little bit later on when we get to reliability and validity. But I want us again is developing our layers of critique to consider measurement. Okay, that's going to be our next section. Let's talk about measurement now, because we have to get the numbers from somewhere. So we have to measure things and people to get these numbers. If it's one of the things I've learned in my academic tenure as a researcher, it's that measuring is really challenging. Full stop. Measurement is challenging. Some things are easier
to measure than others, that's for sure. I mean, I can measure weight, I can measure height. We have tools and instruments that have been around for ages, that have been tested, tried and true. But some aspects of measurement, especially when we start getting into the sociological and the psychological sciences, are much more challenging. Like, how do you measure intelligence, for example, right? How do you measure an attitude? How do you measure a belief? Right? These are very abstract concepts. And these things actually fall across many disciplines. So this is not just linked to psychology. We see it in the health sciences. We see it in the kinesiological sciences. We see it in business. And so some of the things that we measure that are challenging fall across all disciplines. We just need to know that measurement is challenging. And because measurement is challenging, and because we get the numbers from the measures, measurement has implications for our statistical machines that we use, or our statistical formula that we use. Remember that statistics can only use the numbers that are given to them. And I think I've termed this earlier, garbage in, garbage out, as we're going to see as we move forward and take a look at how we measure things. So in the social and psychological sciences, and even in the kinesiological sciences, we like to think that we're measuring people, but we're not really. Really what we do is we're measuring aspects about people and aspects about persons. We like to measure things, for example, like attitudes, physiological responses, even productivity if you get into the economic side of things. And so we measure attributes and aspects about individuals, and we somehow kind of come to some sort of conclusion about individuals based upon these aspects that we measure. And so Pettigrew has a definition down below here. Pettigrew wrote a classic textbook in measurement theory, and he describes what measurement is and how we use it. It's a process of description, really. But there's some action terms with measures. We differentiate using measures. Who's taller than who, right? We use measures to make predictions about things. We use measures to explain things away. And so measures are quite important. So extending from that previous slide, again, just to kind of reiterate, we measure aspects and we measure attributes. And we collect a bunch of measures of individuals, and then we kind of take all those measures together and try and explain the person as a whole. Now the thing is, we know we're not going to explain the person in their entirety, of course, but we can explain perhaps part of that individual if we're involved in. Okay, so what if I gave you a box and I said, measure this box? You'd kind of look at me funny. What do you mean, measure the box? I said, yeah, measure the box. Here's your task. Throw a box at you. Here you go, measure the box. Well, you have all the tools because you have a lab, and you said, well, we can start with, here's a tape measure, and I can measure the height of the box. That tells me something about the box. Right? You could measure the length of the box. That gives you another piece of information. You could even do the width of the box. And if I have those three, first degree measures, if I combine some of them, I could actually get the surface area of the box. Now I've got two-dimensional measures. I could even go to 3 dimensions and measure the volume of the box. I could even go further, right? If I have a scale in my lab, I can put the box on the scale and measure the weight. I could take a look at the texture of the box, the color. There might be some markings on the box, perhaps a label of some sort. And you would tell me these things about the box. But the thing is, you could tell me these things about the box, but you're still only measuring attributes about the box. You're not really measuring the box. Right? This is the challenge with measurement. I mean, if it's hard enough to do this with a box, how hard is it when you actually measure things like, for example, intelligence? Yikes. Like, how do you have to come up with a definition of intelligence in the first place. And the reason why I tell you these things is because it allows us to begin to, even if you've never even taken statistics, you can begin to take a look at how they got the measures in the first place. And I'm going to show you later on, when we get to reliability and validity, in the course, what you can look for to take a look at what I call the robustness of the measures that so we've done this chat on measurement, and it is a bit of an academic exercise, of course, yet it's a necessary one. And why is that? And here's the why. Statistics are only as useful as the measures used to obtain the data. I'll say that again. Statistics are only as useful as the measures to obtain the data. I said before at the beginning of this part of the presentation that it's the garbage in, garbage out motto. If my measures are not robust, I can't really depend heavily upon these statistical findings because the measures might be poor. I might not be measuring what I say I'm measuring, or the measures that I'm used to measure what I think I'm measuring aren't that great, and there are better measures. And if I have poor measures, I introduce things that are called errors into my numbers. And a statistical software program is not going to ask you questions on how you got the measures. It's simply going to run with the numbers, and it's going to give you an output that you have to interpret. And this is why why we have to be careful with scrutinizing measures, whether we're critiquing a journal article or whether we are the ones doing the research. We have to be aware of how we are measuring. Are our measures, that's really hard to say, are our measures robust? And there's always going to be limitations, of course, and we can acknowledge those limitations, but we need to be transparent with those. Okay? Measures that are not valid or reliable can reduce confidence in the research findings. And we'll get to validity and reliability a little bit later on in the course, but this is something that we need to be aware of. So here are take-home points for the measurement section, and then we'll move on here. Number one, measurement is challenging. It certainly is. How we measure affects the quality of the numbers that we use, right? So I've given you some examples here. Is what we're measuring really what we are measuring? Is this the appropriate technique? Are the research staff trained to gather these numbers? All these types of things, right? At the end, it's going to be about quality. Quality measures count, garbage in, garbage out. And I just noticed that rhymes. That's fantastic. Look at that. So heading into our third section here, we're going to describe the types of statistics that we will be working with. We need to characterize those, and we're going to keep it simple. We're going to characterize them either as descriptive statistics, right, which is kind of the soft part of our scaffolding. It's the easier part to a certain extent. And then we're going to describe what inferential statistics are. And inferential statistics are a little bit more complicated in the sense that they're kind of linked in with sampling. And sampling is another part of research methodology. And so I think we need to talk a little bit about sampling. I know this is not a research methods course. I get that. At the same time, this is about statistics in context, and we need to address sampling because later on we're going to find out how sampling affects the numbers and affects our inferences. How we gather data affects our statistical conclusions that we make, and it's quite important. So that's what we're going to do. We'll talk about descriptive statistics, inferential statistics, and I'm going to dovetail into sampling. So I'm not going to talk about anything on the next slide because it's an intermediate slide. So descriptive statistics are really helpful when we're dealing with large volumes of numbers. Right? What do you do with this? I mean, what if I gave you here's a sheet. I have 12,000 individual numbers on there. It's 4,000 Trinity West University students. I've got their height, weight, and age. And I said, can you make sense of these numbers? Even if they're organized into their columns. Yeah, here's a column for height. Here's a column for weight. Here's a column for age. And I ask you, summarize this for me, right? You look at me and go, where do I go? Now, the thing is, after you take a course in Psych 207, you know exactly what to do. You'd apply descriptive statistics, and there's specific ones. And we're going to do that in Chapter 2. It's actually pretty straightforward stuff when you think about it. So this helps us collectivize them and maybe boil these numbers down into one or two that we can use to give an overall description of these 12,000 numbers that we have. More specifically, descriptive statistics allow us to simplify things. Yes, we can do some level of interpretation, but a lot of it is is simply organization and simplification, right? It helps us make sense of the numbers. So our second aspect of our building our scaffolding of understanding of what statistics are is inferential statistics. And I have a definition here on what an inference is. It's not my favorite definition, but I guess it'll work. And we can describe an inference as a process of moving from the acceptance of some propositions to the acceptance of others. It's okay for a definition. I think that the key part there is the moving part. That's actually the key. That's the verb there. The moving part is the important part of that definition. But an example might be a little bit better to describe what an inference is. And it's this: if you live in the Lower Mainland, you know that a lot of our weather comes from the ocean, right? Those are the prevailing winds. And if you or I were outside and we looked to the west and we saw this big bank cloud of dark clouds coming over the horizon, right, we would probably infer that, you know what, it's going to rain on us soon, right? So the first proposition that we accept is we see dark clouds. Here they come and they're moving towards us. It's getting darker and it's getting cloudier. We accept this because we're actually observing it. Now, what we have to accept in part, I don't use the word by faith, but we kind of make an inference or perhaps a prediction or perhaps a conclusion or an interpretation of the dark clouds. And that interpretation is, you know what, we're probably going to get rained on. Now, that's despite the fact it's not raining on us yet. We are seeing something, right? That's the first proposition or the first observation that we see. And from that, we infer, yeah, we're going to get rained on. Now, we don't know for sure if we're going to get rained on. And so sometimes you might say, well, what are the chances we're going to get rained on? And someone might say, well, there's an 80% we're going to get rained on. Someone might say there's a 50% chance. Someone might go, no, there's a 99% chance we're going to get rained on. So with inferences, we can actually begin to put numbers in terms of, or things like likelihoods, right? There's a probability of something occurring. Now, we don't know if it's going to happen or not. Right, and this is the inference. We see something happening that we can actually measure. I can measure, the grayness of the clouds. I might be able to measure wind temperature, all those types of things. Here it is. But I don't know for sure if it's going to rain because rain is something that might happen in the future. Right? And so inferences aren't always about future predictions. Sometimes they could be predictions in the present. Right? Or we call those characterizations of things or generalizations of things, right? And we make a generalized comment based upon something that we see that we're trying to apply to a larger whole. That's an inference. So taking us back to persons and inference here, again, in the social sciences, we're interested in inferring things about people, right? And to do that, you've got to get people into studies, you've got to get information from people. And so what we do is we take a sample of individuals and we might query them on something, right? We might be interested in, attitudes towards the U.S. and Canada border closure during this COVID crisis. And let's say that we were interested in Trinity Western University students' attitudes and perspectives on that. And so, there's about 4,000 students on campus, and so we go and we take a small sample of those 4,000, and 40 people volunteered to give up their attitudes and perspectives. And so we measure those things, those attitudes and perspectives, and then we kind of use descriptive statistics and we kind of conglomerate things and summarize this information. And then from that, we make an inference. And what we're saying with an inference is this: the sample that we have, the small sample of students from Trinity, 40, is going to represent the 4,000. Now, you might go, whoa, 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 that's a pretty big jump there. And it might be. I mean, 40 out of 4,000, that's only 1% of the population is supposed to represent the entire population? Hold on a second. And so this is part of the issue. And this is why we have to talk about sampling. Not only the size of the sample, but how we get the sample in the first place. Because we're not really interested in what the sample has to say. We're really interested in what the population has to say. But it's pretty hard to measure the entire population. So this is why we have to use samples. And we'll define what a sample is in the slides coming up. I think I already covered this in the previous slide here. And again, it has to do with the sample representing the population. And so part of the inference, again, includes making predictions or generalizations. We actually project these things onto the larger population based upon what we have gathered from the sample. And that is an inference. That's what an inference is. We take these things that we've learned from the sample and we generalize them to the larger population. And this is the second part of statistics. And this is where it gets a little bit tricky, a little bit trickier. And this is why I have a fourth section in this initial PowerPoint, where we describe this relationship, at least in part, not in whole, but this interaction between sampling and statistics. And it's sort of like the measurement and statistics relationship. This all goes back to the data that we gather. Okay, now this time it's not a measurement issue. This time it's a sampling issue, and the issue is a little bit different. But what I want to do in the next few slides is define what a population is, define what a sample is, describe a couple of things that we do, which we call random samples or random allocation. These are important things for you to look for when you read journal articles. And then we'll get into something called a sampling bias. We're not going to get into how to fix these things, but these are some things that you should be aware of. So like I'd mentioned before, in research, we like to make broad generalizations about populations. Now, when we think about population, we might think about, the population size of Canada, which is around about 38 million people, or the United States, which is around about 340 million people. But a more precise definition of a population, at least for us, it's this. It's a well-defined group of people, or objects, doesn't have to be people, that share common characteristics. So here's some examples of that, right? It might be Canadians between the ages of 18 and 40. That's the population that I'm interested in. Right? Researchers always will define their populations ahead of time, and there's a bunch of different reasons why, but they'll put boundaries on that. And they'll give you reasons as to why, we're just interested in surveying Canadians between the ages of 18 and 40. If you're above the age of 40, we don't care. We're not interested in that. So our population parameters, right, or our population boundaries, you have to include this. You've got to be between the ages of 18 and 40. Right? It could be something related to economics or income. So we're only interested in U.S. citizens who make between $40,000 and $60,000 per year. Okay? It could be something even more specific. We're only interested in researching British Columbians who have experienced some form of spinal injury. And so the population definition is all based upon what the researcher wants. And so the researcher will set boundaries and parameters around the population. They actually define the population ahead of time. So that's what a population is. Now, the problem with researching populations is that they can be really, really large. There's all kinds of logistical barriers to researching everybody in a very specific population. As a matter of fact, it's almost impossible to measure every person in that population, even in Canada, right? I mean, if you wanted to take a look at what the average income is in Canada, you might think, well, that's fine. Just go talk to the Canadian Revenue Agency. Everybody's got to file taxes. Sure, everybody needs to file taxes. That's the law, but not everybody does file their taxes, right? At least on time. And so you're always going to miss a few. Now the thing is, if it's tax-related stuff, you're probably going to capture most of the population. But there might be 100,000 that you don't capture, right? For whatever reason, they didn't file their taxes, or they're on the lam, or who knows, right? They might have forgotten. And so you're not going to have the full population. And that'd be an easy thing to measure because the CRA has this fantastic database. What if you're the one who has to go out and, number one, define your population and then try and take a sample from that population? You've got to go find these individuals first. It could be quite challenging, right? It could be quite challenging. And so measuring populations is challenging because of these barriers. There might be too many people. Good gravy. My population is 1 million individuals. How am I going to measure? How am I going to survey 1 million individuals or measure? Right. So that's the segue here. And so a sample is what we call a smaller subset of the population, a smaller size. Right? So if you've got 1 million people, you might want to go, well, I can't measure 1 million people, but I've got enough resources and funding and time to measure maybe 10,000 of those million. And you go out there and you reach in there, whatever mechanism you use, and it's really hard to do, and you find 10,000 people, and these 10,000 people you sample. Now the thing is, the sample that you choose, you don't really choose it. There's a methodology as to how to get a sample. But your sample is assumed to be a subset or have the same characteristics of the population that it came from. That's an assumption that we make every single time. When you read a journal article, we had a sample of 30 individuals who participated. Those 30 individuals are assumed to have the very same characteristics from the population that was defined by the researchers. And here's where you start getting some problems. How you go about getting that sample into your research method or into your research program can dictate whether or not that sample actually does represent the population or not. There's some things that can happen along the way, and we actually call those biases that can filter into how you go and get that sample. At the end of the day, you're going to have your sample, you're going to measure them, and you're going to say, well, our sample, we're going to make an inference from our sample to the population, but unbeknownst to you, right, and it might have been a mistake or an unconscious error, the way you gathered that sample, man, that sample actually in real life does not represent your population. And these are some of the challenges that researchers have to go through. So again, here's kind of a follow-up slide or an extension of the previous slide. You know, in the red circle there represents the population. That little blue circle there is the sample that we pull from the population. That sample is supposed to represent the population in terms of the specific characteristics that you're interested in if you were the researcher. And so there's some aspect of idealism here and a certain aspect that we assume the sample represents the population. And so from this, whatever we find in terms of our measures from the sample, we infer to the population. So here's a question. You've drawn a sample of participants from the population of Canadian medical doctors to survey their attitudes and opinions about the use of medicinal marijuana for pain management in patients with fibromyalgia. Okay, that's a decent research question. How can you be confident that the sample of doctors drawn that you did, without even going into the mechanisms, we're not going to talk about that right now, actually represents the population of Canadian doctors? Well, there's a few things. Number one, you have to know the size of your sample, which we'll get into later on in statistics. So we'll leave sample size out for now. But you know, how could you be confident in that, right? You know, part of the answer is how we draw that sample to begin with, and I want to talk about randomization with you. That's the only one I'm going to talk about. There's all kinds of stuff on sampling theory and methodology you can take in a research methods course, but I do want to talk to you a little bit about randomization because that is something that you can look for when you read journal articles, and it plays an important role in terms of inference, right? One of the first things that we do, however, is we try to, in order to get an accurate sample, is we attempt to eliminate what is called sampling bias. So I want to talk about sampling bias with. So a sampling bias is when the attributes that you're interested in, right? These are the population attributes that you're measuring from your sample, don't actually represent the population attributes, right? So let me give you an example of that. Let's say that unbeknownst to you, the height of your population, the average height of your population was 5'8", but your sample's average height is 5'4". So that's substantially lower, substantially less than the actual height of your population. And the funny thing about sampling is, well, how do you ever know then? That becomes one of the questions. And there's ways to get around that, with combining statistics and combining research methodology, you can do some things so that I call it, you're in the pretty darn sure category, you got it right. But sampling biases can occur. Now, these biases can be conscious, they're pretty overt. Sometimes they can be unconscious. They may happen without the researcher's intent, right? Or the researcher might do something that So one of the ways you can reduce sampling bias is to use a process called random selection. And without going into the mechanisms or even the description of what randomness means, but here's a definition for you. Random selection is this. It means that it's a process wherein, when you're sampling, everyone in the population gets a chance at being selected for your research project. That's what random selection is. If you want to really simplify and boil it down, it's a series of procedures, there's more than one, wherein everybody in that population gets a chance at being part of your research program. That's probably the best way to describe random selection, at least for us. So this is something that you can look for when you read a journal article. You can take a look at how they got the people in the study. If you see the term random selection, or in the next slide we'll talk about random allocation, those are good little green check marks for you to say, okay, this is going to be important for the statistics, and this actually helps reduce the risk of sampling bias. Now, what I didn't say in the previous slide is randomly selected samples from populations are really hard to do, and they're actually quite rare. And that's okay. I mean, that's just one of the limitations of what we do in research. But there's another thing that a researcher can do to actually help with sampling and help with inferences, and it's called random allocation. And random allocation is this. This is when I have a sample. Let's say I've got a sample of 100 individuals I pulled from a population of, say, 50,000. And I wanted to put some in a control group where they receive no treatment or no intervention, and the other I put into the treatment group. And all random allocation means is that all the participants in the sample, right, had a chance of either being in the control group, and they had a chance of being in the treatment group. And the procedures that did it, some were allocated to control and some were allocated to treatment. But it was done randomly and without the researcher's influence. A lot of times we do random allocation by using computer programs. You can have what's called a random number generator. You can assign individuals that way. And there's a bunch of different ways of doing it. But random allocation is something else that you can look for in a journal article that tells you more about the robustness of the sample in terms of how it's actually going to represent the population. So why is randomization so important? Here's 3 reasons why we attempt to do randomization, why you should look for it as good flags or green flags in terms of the robustness of the confidence you can place into a research journal's findings. And the first one is this: it helps ensure the representativeness of the sample to the population. Again, that all goes back to inference. Does the sample represent the population? Okay, if you've got a random sample, that's fantastic. That's actually very, very helpful. It actually builds greater confidence that the sample represents the population. The second one is this: it shows that the researcher was unbiased in the selection of the members of the population. And researchers will actually state this. They'll say, I had someone else actually do the selection for me and randomly allocate them into two different groups, control and treatment. And here's how we did the randomization procedures. So everything is described in a research journal. And the third one is this, and this may not make a whole lot of sense now, but it might a little bit later on, is you want to, randomization, or in particular random allocation more specifically, helps equalize the characteristics among the groups in the research studies, especially if you've got like a control group. These are the groups that might not receive any treatment, and you've got a group that actually receives the treatment. Let's just say, for example, you were examining the level of pain in individuals with fibromyalgia. Maybe this might be lower leg pain, for example. So you randomly allocate them into the two groups. The control group, they get a placebo treatment, and the experimental group, they actually get the real treatment. This is the thing that you're really interested in. And so what you do to kind of get a sense of levels of pain is you actually give them a pain scale. And what you find is that the pain, lower leg pain in each group, was actually pretty similar to start with. You know, group A, the control group, their level of pain on a scale from 1 to 10 was about an 8. And in the treatment group, you know, on a scale from 1 to 10, their level of pain was 7.9. It's pretty close. Random allocation actually helps with that. It actually helps equalize the groups. And so now you've got more of a level baseline to start with, especially if you think that your treatment, you know, treatment group B, their pain is going to be reduced greater compared to, say, some level of a placebo treatment. Okay, so how can we summarize this section here? Because we're pretty much done. Number one, we want to answer research questions about things that we think are important, right? I mean, this is what we see in journal articles. Researchers are finding gaps, and they're trying to fill these knowledge gaps with research questions. Statistics fits into this because statistics help us understand behavioral phenomena and other phenomena. Now, we haven't got to the interpretation side of things yet, but we know that they do help us with this. However, statistics don't operate in a vacuum on their own. Rather, they occupy a specific place in research design, as we've seen. Further to that, some of the interaction between statistics and the research design has to do with measurement, right? Measurement values, garbage in, garbage out, and also sampling procedures, which you will take in a research methods course. And both of these elements of research design interact with statistics, and they influence statistical outcomes. To answer our research question, we need to get hold of some of these attributes and characteristics of interest, and we need to measure those. And we call those attributes and characteristics variables. Variables we'll unpack a little bit more in Chapter 2. There's some layers to variables there. But to obtain these measures, we need to get a sample from the population. Ideally, we'd love to use random selection. A lot of times we can't use that. We might use something called convenient sampling, which is okay. It's totally fine. But when we have our sample, and if we have to divide them up into smaller groups to do some testing and to do some more research, we can use random allocation to divide our sample up into smaller groups. And these procedures are ideal in the sense that they actually help reduce the biasing of the sample, so to speak. And now finally, we've actually gathered our measures from our sample. We can begin to apply our statistics to answer our research question. And the two basic types of statistics that we use are either descriptive, which are the summarization of information, and also inferential, which is where we do some aspects of either generalization or prediction. This is inference. Again, we're making inferences about our sample to the population at hand. Okay, so that concludes our first lesson in statistics. And again, there was no math. Isn't that great? No math. But there's some complicated stuff here. There's some layering to what we're doing. And we had to approach statistics in its context and to see where it fits into the research design, and to make two notable things we need to consider. Number one, measures are important, garbage in, garbage out, and sampling, how we sample. Both of these play a role in formulating our statistical conclusions.